Hi, my name is Kent Lee and I teach computer science at Luther College. In the last couple of videos, we've been learning about binary numbers and how to convert from decimal numbers to binary numbers, and also how to represent negative numbers as binary numbers. In this video, I'm going to present an algorithm for converting from decimal to binary, and it uses some principles of binary numbers that I hope to make clear with a video that I have, an animation that I have put together here that we'll watch. So in this animation here, we have the number 42 represented as a binary number, 0, 0, 1, 0, 1, 0, 1, 0. So this binary number, we're going to do some things with it, and in particular we're going to divide by 2 here. Dividing a binary number by 2 means to copy, basically what you have to do to divide by 2 is copy the number, shift all the bits to the right one, and repeat the leftmost bit, throwing away the rightmost bit. So think of this as a byte. There are 8 bits here, and if we're going to divide by 2, we're going to shift all the bits to the right and throw away the rightmost bit. And again, repeating the leftmost bit if you watch it here as we go. This process, we're doing this over and over again. In fact, we're repeating this process 8 times, and that's part of the algorithm. We're going to divide a binary number by 2 8 times to find out what its binary value is. So, and we can just kind of watch the process here. So we are down to the number 2 right now. That's 1, 0. Divide by 2, that gives us 1. So that's the binary number 1. And dividing 1 by 2, this is integer division, is going to give us 0. And we're going to throw away the 1 there as we shift to the right. So we do this process 8 times, and we end up with 0 at the end, of course. And we have shifted all of the bits, basically. All of the bits that were in the original byte are shifted out of the byte. Now, if we're going to do this in Python, we're going to use a couple different operators for doing this in Python. So we'll start with the number 42 again, 0, 0, 1, 0, 1, 0, 1, 0. And if we want to know what the rightmost, well, if we want to divide by 2, first of all, we'll copy it down. But in Python, dividing by 2 is 2 slashes, so a double slash. So the double slash is the integer division operator in Python. And if we want to save that rightmost bit, that's the mod 2 operator. So if we take the original number 42 and mod it by 2, we're going to get the rightmost bit in that number. So you can see there that the rightmost bit here, this rightmost bit, is this bit right here. So we're going to repeat this process. Dividing by 2 shifts everything to the right. Mod 2 of the original number gives us the rightmost bit. So this bit right here is this bit right here. And we just repeat this process 8 times. So this is kind of interesting to see. We're repeating a process over and over again. That's an algorithm that we're following here. These are the steps of the algorithm. Mod 2. Mod is the percent operator right here, and div2 is the 2 slashes. And again, that's integer division. You can do other kinds of division, what's called floating point division in Python as well, but integer division is 2 slashes. So we'll repeat this process 8 times. Got a couple more iterations of the algorithm to go. An iteration is 1 time through the steps that are being repeated. So a few more iterations to go here. Okay. We're getting pretty close. And so we've got 1 mod 2 is 1, that's the rightmost bit, and when we divide 1 by 2, it's 0 with the remainder of 1. Okay. And that's our 8th time through. So the last time through, we're going to have all zeros here. Of course, we've had all zeros already for a little bit, and mod 2. Now here's what I want you to notice at this point. So in this animation here, we've saved the bits, the rightmost bits, and if we read them from the bottom up, 0, 0, 1, 0, 1, 0, 1, 0. That's exactly the number 42, and it kind of makes sense because each time through the algorithm we shifted all the bits to the right, and the mod 2 always gives us the rightmost bit. So these would be all of the bits of the number right here, of the original number, just gathered up one at a time. So again, we read it from the bottom up, 0, 0, 1, 0, 1, 0, 1, 0, and that is our number 42. Now, what's interesting about this is that this is the number 42 right here. It is the binary representation of 42, but nevertheless, it's 42. Whether I write 42 as 42 or whether I write it as this, it's still 42, either way. So, what's interesting about that is that if we go and look at the number 42 and write it down as a decimal number and do mod 2, the mod operator again is going to really be the rightmost bit, and the rightmost bit is whether it's odd or even. So 42 mod 2 is going to be equal to 0, but 21 mod 2 is going to be equal to 1 because 21 is odd. 10 mod 2 is equal to 0 because 10 is even, and 10 divided by 2, of course, is 5. So 5 mod 2 is equal to 1. Okay, and 5 divided by 2 is going to be equal to 2, with a remainder of 1, of course. So 2 divided by 2 is 0, or 2 mod 2 is 0, and 2 divided by 2 is 1. And 1 divided by 2 is 0. And 0 mod 2 is, of course, 0. And look at this. If we read this from the bottom up, we have 0, 0, 1, 0, 1, 0, 1, 0. So in this animation that we have here, we can see that this algorithm works perfectly well both for a decimal representation of 42 and a binary representation of 42. After all, 42 is 42 whether it's represented in decimal or binary. And we have an algorithm here for converting it to binary by looking at the remainders after doing integer division, and that's called the mod operator again. So modding by 2 gives us the remainders after dividing by 2. So again, read it from the bottom up, 0, 0, 1, 0, 1, 0, 1, 0, and that is the binary representation of 42. Now, it is interesting to note that while binary is what we represent all values in the computer as, all values are represented in binary in the computer, programmers oftentimes do not like working with binary because it's a little wordy having to deal with all of the bits of a binary number. So there are other bases that we might use as programmers, probably not right away here, but it doesn't hurt for us to know a little vocabulary about some of these bases. So 42 here, this is a base 10 representation. Of course, 0, 0, 1, 0, 1, 0, 1, 0, that's a base 2 representation. It turns out that for programmers, base 16 is also a representation that can be useful. So here we have the number 42 base 10 and its binary representation. And if we would like to convert this binary representation to what's called hexadecimal, which is base 16, then we need to somehow understand what hexadecimal is all about. And I've drawn a little legend over here for us to help us understand what hexadecimal is all about. So if I have the decimal digit 0, that's equal to 0, 0, 0, 0, and 1 is equal to 0, 0, 0, 1. Those are easy enough. 2 is this way in binary, and 3 is this way in binary, and we have all the way on up through 9. So 9 is, the decimal number 9 is represented as 1, 0, 0, 1 in binary. Powers of 2, 2 to the 0 plus 2 to the third. Now, in hexadecimal, these last 6 here, 10, 11, 12, 13, 14, and 15, need to be digits in hexadecimal. So we can't represent 10 as 10. So rather than representing 10 as the number 10, what we're going to do is erase these here in our legend, and we're going to rewrite them here. We're going to provide a different representation for them. So instead of having 10 be represented as 1, 0, what we're going to do instead is represent 10 as the letter A, and 11 as the letter B, and 12 as the letter C, and 13 as the letter D, and 14, of course, is E, and 15 is F. Now, the advantage of doing that is that you can see here that all of the binary representations of 0 through F involve 4 bits. So this is the advantage of hexadecimal. Hexadecimal being base 16. 16 is a power of 2, and that means to convert from binary to hexadecimal, it is very easy. We can just take 4 bits at a time. So we take those 4 bits, and then we take these 4 bits, and we can convert this binary value to hexadecimal very, very quickly by using our little legend over here. So 1, 0, if I look over here, that's just 2. So this is 2. And 1, 0, 1, 0, let's see if I look over here, here's the pattern 1, 0, 1, 0, so that's A. So 42 base 10 is equal to 0, 0, 1, 0, 1, 0, 1, 0 base 2, which is a little wordy, or just 2A base 16. So that's the advantage of hexadecimal. If you have to convert back and forth between binary and decimal quickly, then it's binary and hexadecimal. It's advantageous to have this hexadecimal representation. It's less wordy than binary, and it's very easy to convert back and forth between binary and hexadecimal. So that's it for this video. In the next video, we'll talk about the ASCII codes and what they mean for us.